pi, which should be equal to B dot dA. Just if we simplify, this is going to be just assuming that it's a long solenoid. If it's a long solenoid, how do you express the magnetic field? For a long solenoid, B is mu naught n, where n is the number of turns per unit length, times whatever current flowing in the solenoid. So if this is the wire, and if this is the solenoid, so we connect this one to the power source. N is the number of turns here. That's the number of turns per unit length. And if I assume this is the z axis, then what's going to be the direction of the magnetic field? Assuming that that's the flow of the current. So if that's the flow of the current, it goes like that. It goes into and coming out on the side, the current. So the magnetic field is going to be along the z-hat direction. Huh? Right? Yeah. So just think that you have this solenoid and the current is flowing like that. So you just wrap it around the direction of the current, you come into the direction of the field. So if we assume that this field is going to be a constant over this area, then you can find the flux pi is going to be mu naught Ni over whatever the radius of the circle. That's going to be pi a squared. So that is at a little time t. So there is a change in flux delta pi equals to mu naught Ni pi a squared with a minus sign. All right. Now the flux is increasing. So what should be the direction of the induced current? So whenever there is a change in this flux, then there is going to be an induced current. And what should be the direction of that induced current? Yeah, because the flux is jumping from 0 to this value, right? So that's the initial, therefore that's the final. The flux jumped, so and the direction of the external magnetic field is in the positive z direction. So you need an induced magnetic field that points in negative z direction, right? Yeah, downward. So in order to get that kind of induced magnetic field, the current must flow. Yeah. So you would have a current flowing in that direction. Now you have an induced current, and there is interaction between this current and the magnetic field of the solenoid. So for that, I have to assume the real form or the real direction of the magnetic field of the solenoid. So in reality, the magnetic field on the solenoid here is directed, if you consider 2 points, one here and one here. The direction of the magnetic field at this point, due to the solenoid, is going to be like that, right? It's going to be curved and like that. So the direction of the beam. And if you assume this angle is theta, and this angle is theta, and you know, in one of the homework problems, you did something similar to this. So when you decompose it into two vectors, you have this vector and that vector, and this vector and that vector. And now if you just look at the force resulting from each of these components, if you look at the magnetic field due to this, what's going to be the force due to this one? So if you use the right-hand rule, you have a current coming towards you, so current coming towards you, magnetic field this way, force is going to be upward. So you have F on this side upward. So that's F. And on this side, current going in, magnetic field is this way. So current, field, so you have a force upward. So we are talking about the force due to the induced current. But for the other components, you can easily show that they are going to cancel out. Because if you consider this component of the B field, the force due to this component of the B field, you have a current towards you, a B field up, so I crossed, I is towards you, B is up, so I crossed B, you get a force in which direction? Toward the center, right? So you have a force in this direction. Are you following me? Huh? So just think a current coming towards you at this point, and we are talking about the component of the B field that's normal to the ring, so which is pointing along the Z direction. So you can think of, you have a B field component along the Z, and a current that comes in the positive X direction. Okay? So I with B, you get force in that direction. And at the same time here, if you look at this point, you have a current going in, magnetic field up, so I cross with B, you get force in this direction. So these two cancel out, and you would have a net force that push the ring upward. Okay, another interesting example here. Suppose you have a line charge that's glued onto the rim of a wheel of radius B, which is then suspended horizontally as shown in the figure below, so that it is free to rotate. The spokes are made of some non-conducting material. In the central region, out to radius A, from here to radius A, yeah, okay, so I think it should be up to this. So from the center up to A, up to a certain distance, you have a magnetic field B0 pointing up. Now, someone turns the field off. You instantaneously cut off the B field. So what's going to happen? It will start to rotate. Why does it rotate? Okay, the question is, explain what's going to happen, and obviously it's going to rotate, and I'll show you in a moment why it rotates. And the second part is to show that it's angular. If there is a rotation, that